Hi folks, today's topic is the fundamental theorem of calculus. Every branch of mathematics has its own fundamental theorem, so automatic A to anybody who can recite in this corner right here, the fundamental theorem of algebra. How'd it go? No, without looking it up. If you remember the fundamental theorem of algebra, if, how about this? This is quicker. A polynomial with degree n has n complex zeros. Oh, now you're like, oh yeah, shoot, I remember that. Okay, so fundamental theorem of algebra. So today we're talking about the fundamental theorem of calculus. So this is going to revert back to what we talked about last time with integration. So it's basically the idea that you're tying integration to derivation. So we've got our two branches of mathematics, differentiation, that's what we covered in the first half, all those derivatives, and now what we're doing, which is called integration. So it's this idea, so Newton's teacher, Isaac Barrow, was the one that discovered that these two processes are inverses of each other, which we probably kind of already assumed since we called that our first lesson anti-differentiation. But at the time, it was a pretty big deal, right? They didn't understand already. Somebody didn't already do all the heavy lifting like they did for us. So on the shoulders of giants, right? So in the same way that division and multiplication or add and subtract or root and exponent undo each other, integration and derivation undo each other at the same time. Okay, so a couple of things to point out. So that's what we call the fundamental theorem of calculus. If you think about it, when we did derivatives, what was our fancy notation for doing a derivative? dy over dx. And now we're doing integration. Integration is the integral of f of x times, we don't usually write that times symbol, but it's there, dx. So, I mean, even at its most simple level, derivation is division, integration is mult. So they undo each other. Kind of interesting how they connect. So here's the fundamental theorem of calculus. This is the first part. Corpy calls this the first part. I guess he referenced in his video that lots of people call this the second part, but whatever. So we're going to get to the second part later in the notes. So remember this notation. F is our function. The antiderivative, okay, is called capital F. So when I integrate f, now we've already got a notation for deriving. So when we derive f, we get f prime. So when we integrate f, we don't have a symbol for that. So that's what we call this big capital F here. If f is continuous and capital F of x is the antiderivative, then the integral, so this is what we call, again, let me get my colors here. This is what we call a definite integral. It's definite because it gave us our boundaries. So we don't have to worry about writing plus c, and we'll talk more about why we don't have to write plus c. We have to write plus c when they don't tell us over what area we're trying to define. So the integral from a to b, this is read the integral from a to b of f of x dx is the antiderivative from a to b, which is really take this number, plug it in for x, take this number, plug it in for x, and subtract those two values. Okay, a couple of things I want to point out before we get into an actual example. Kind of interesting here. Notice that this says if f is continuous, then we can do the integral, as opposed to before, pause. I would like you to go back and finish this. Well, it'll only take a second. If f is differentiable, comma, then what can we say? Well, then we can say f is continuous. Hopefully you remembered that. Notice what this inverse is saying. If f is continuous, then f is integrable. Not my favorite word to say. So you kind of, yet again, it's pointing out this relationship of inverses. So here we're talking about f being differentiable, therefore continuous. The contrapositive, is that what that was called? I don't remember. You'd have to think back. If f is continuous, then f is integrable. Okay, so why does this work out the way that it does? Well, we'll talk about it in this first example. No, let's just do it up here. I've got enough room for it. Okay, so let's go back to this spot right here. When I integrate little f, I get this thing called big F, right? But this big F should have a plus c at the end of it. So basically, this should really say f of b plus c minus, then this should really say f of a plus c. Right? When I integrate, there should be a plus c right here. So this should say f of x plus c, but when I plug in little b and when I plug in little a, I would get this difference. Now, if you look at these two things, what's going to happen to those c's? Those are going to cancel out. That's why we don't need to include the c. Whatever the c is here would be the same plus c, and then it would be subtract c if you were to distribute. So the constant doesn't matter when you have a definite integral. So you have to pay attention to when you have a definite and when you don't. All right, this is pretty straightforward down here. Evaluate the integrals using the fundamental of theorem of calculus, part 1. So I want to integrate this. Technically, you should probably split this up into two separate integrals and all that crap. We can integrate this all in one mighty move. So this is how the notation works. I'm going to take this and I'm going to integrate it. So the integral of e to the x is, hopefully you said e to the x, minus the integral of 3, that's just a constant, so it's going to 3x to the 0, so it's going to put that constant in there, would be 3x. And then at the end, you write 1 to 3. Now, if you just have one term, you can just write the bar at the end, but when it's more than one term, usually we write some brackets around it. All right, now we still have to actually evaluate this thing. So now I'm going to take this, I'm going to evaluate, plug 3 into it, then plug 1 into it. So my first would be e to the 3 minus 9 minus, it's f of b minus f of a, minus e to the first, 3 times 1 is 3, which we can then clean up. Oh, not much. We can't really clean up much, can we? So this would look like I've got e to the 3 minus e to the first, which is just minus e to the first, just e. Then minus 9 minus a negative, which is really an add, becomes subtract 6. So e to the third minus e minus 6. All right, looking at the next one. So I don't know if your math voice is hollering at you. This is one of those for my AP test takers. You got to memorize this. If you're not sure, go back, I think it was to 4.1. There's a list of a bunch of integrals there. I've already looked it up. I don't remember it either, but luckily I don't have to take a AP test in May. But the integral of this ends up being, actually, go look it up first. Go look it up. Pause and go look it up. Okay, if you're one of those AP kids, you got to memorize them. Man, it's not probably going to be on a free response section, but it will be in the multiple choice. I can almost guarantee it. So when I integrate, the constant's a constant, so I don't care about that. So I'm going to have a 2. And then the integral of this ended up being sine inverse. And our boundaries are from 0 to 1/2. Okay, now I don't have to worry about the plus c because this is a definite integral. If I didn't, I'd have to write the plus c for a whole point. A whole point on the test is based off of that. So now I'm going to plug these values in. 2 sine inverse of 1/2 minus 2 sine inverse of 0. All right, remember what sine inverse means. Sine inverse means that we need to find the angle at which this sine is 1/2. And remember that sine inverse, if we go back to our old unit circle. So there are two values that have a sine value of 1/2, right? Hopefully, pause and see if you can remember. Hopefully you said pi over 6. And then 5 pi over 6, those both have positive 1/2 values. But remember, sine is defined here and here. Sine is defined here and here, so is tangent. Sine and tangent are defined there and there. And then cosine is defined in quadrants 1 and 2. So we're going to only pick the ones that live in quadrants 1 or 4 for sine or tangent. So that's going to mean this is going to be 2 times the pi over 6 is the only one that's legal, minus 2 times. I'm asking you to find an angle at which the sine value is 0. So that one's pretty easy. If we're only living from here to here, that's going to be also a value of 0. So 2 times pi over 6, the 2 is going to cancel. I would get pi over 3. 2 times 0 is 0. So we would just get pi over 3. Okay. Uh-oh. Try to integrate this. I add 1 to the exponent. That would be 0. We've got a problem. So notice, we're going to leave a little reminder up here. I want to rewrite this, first of all, as the integral of x to the negative 1 really means what? 1 over x dx. And hopefully you remember that the integral of that, now that's one I expect everybody to know. That's not just a AP or a test taker one. I expect every kid in here to know that this is, the integral of this is the natural log of absolute value of x. So when we integrate it, we have to include that absolute value in there. And now that one had a plus c because I didn't have a defined boundaries. Anyway, so we can integrate this. Our integral would be, now here's one that I just have one term. So I would go natural log of absolute x. And then I would just draw this bar from 1 to e squared. If you like putting the brackets around it, it just makes you understand it better. There's no harm in that. It's not even mathematically embarrassing. So you could definitely write it just like this. Okay, now I want to evaluate. I want to do the fundamental theorem of calculus, which means plug in, subtract, plug in. So that would be the natural log of absolute e squared. Do I care about those after all? No, but I needed them here at least. You don't actually have to write them here. They infer that the graders will know that you meant that, but here you must write it. Natural log of absolute 1. I like to write it because it reminds me to write it in the future. All right, so let's think real quick. Natural log of e to the second, the natural log and the e to the are going to cancel. Minus natural log of 1. Well, it's tempting to stop here, but you can actually do a little bit more. Think about, pause after this, how can you rewrite 1 as an e to the? Hopefully you came up with that 1 is equal to e to the 0th, just like anything. So I can rewrite this as natural log of e to the 0th. The natural log and the e cancel out. I get 2 minus 0. 2 minus 0, of course, is 2. All right, let's have you try. I would encourage you to pause and do one of these at a time. I'm not going to probably remember to remind you, but try. Well, this one you're gonna struggle with, and this one you might too. But these two, you should be able to do those without any help. So I would encourage you to pause and try to do this one. All right, let's see how you did. What's a good color? Let's go with some brown, I guess. All right, so I'm going to integrate, add 1, divide, so that's x cubed over 3, minus no x, so that's just going to be 1x. This is occurring from 1 to 2. Now I need to evaluate by plugging in, so this is going to become, I'm going to just plug it into my head, 8/3 minus 6 minus 1/3 minus 3. I got to do some common denoms here. Well, that would be 7/3. It's not going to make it a whole. Maybe I won't have to do as. I'm going to try to combine it like terms first. Let's see if that saves me a little bit of time. So 8/3 minus 1/3 is 7/3. Minus 6 minus a negative is really an add, so that's -3. Now I'm going to go for my common denom. I'm going to be lazy and just write it over the top. That's 9 over 3. 7/3 minus 9/3 is negative 2/3. Good job. Good job. Good job. Okay, next one. As always, the same thing as what we did with derivatives. Rewrite early and often if you can. So I'm going to try to clean this up first. This is the same as the integral of 3x to the 1/2 dx. Don't forget your boundaries if you're talking about a definite integral. Okay, so two parts. The constant I don't care about. That's 3 times. Add 1 to the exponent. So 1/2 plus 1 would be 3/2. And then I need to divide by this. So remember how we talked about you just do a flip and multiply? Now you can either write plus c here, but I recommend going with the bar and writing 1 to 4 because you only have one term. If you like the brackets, actually you can't write plus c. I don't know why I said that. Or you could write the brackets if you like that better. All right, so I'll notice that the 3's, they gone. And then I can start plugging in a chugging. So this would be 2 times 4 to the 3/2 minus 2 times 1 to the 3/2. I like the second one a lot better. Let's see how this one goes. So that's 4 to the, do this. I wouldn't, you want to cube it first, go for it. You can. It actually will work. 64, that won't be too bad. But I would always try to root first and then cube. So 4 rooted, remember that's 1/2 is 2. 2 cubed is 8. 8 times 2 is 16. 1 to the any power, I love that because it's still just 1. 1 times 2 is 2. 16 minus 2 is, how'd you do? 14. Okay, so integral up, boom, right off the bat. My math voice perks up here, says this is one that I would expect everyone to know. This is one of my trig derivatives that we're going to try to integrate it. So I never can remember this direction. So what I do instead is I find an empty space somewhere that I can write the derivatives. So I'm going to encourage you to pause after this, write the function, and then write its derivative. We should have this memorized. So this should be fairly easy to do. Then what we'll do is we'll use that to work backwards to integrate. So go get them. All right, let's see how you did. Let's see, sine of x, their derivative is cosine of x. Cosine of x derivative, it's a so it's a negative sine of x. All right, so I got the two easy ones. Now I'm going to move on to the next is secant. Secant's derivative starts with secant and switches to tangent, all the ones that don't have any cos. So cosecant, negative because it's a and then it starts with the cosecant again, but goes to the cotangent. And then we've got our last one, or last group, I should say, tangent. Tangent stays with the ones that it's not a so it's not going to be one of the cos. And then cotangent becomes negative cosecant squared. All right, so now I want to look down here. I'm trying to integrate secant squared, but I can look back at my list. Who's got a derivative who is secant squared? So when I integrate it, it's going to turn out to be tangent. So then we can come back down here. So this is going to become tangent of x from 0 to pi over 4. Now we got to plug in chug. So this was a trig deriv. So trig, anytime you're trying to integrate something with trig, you want to go make your list of trig derivatives to work backwards. And then, okay, so plug in chug. Try this on your own. You should pause here. This is something you don't need me for. These are those flashcards that we do. All right, pi over 4, that's a 45. 45 is a root 2 over 2, or root 2 over 2. Tangent is y over x, so that's just going to be 1. Tangent of 0, this one's going to take a little bit more work. Tangent sine over cosine. So sine is 0 over 1. 0 over 1 is 0. 1 minus 0, should have got 1. How'd you do? All right, so life gets pretty complicated when you're talking about absolute values. The best way that I've found to figure this out is to break it up. So in other words, I need to figure out where this graph shifts from being positive to negative. So I'm going to make a little sketch. I'm going to start off by just sketching. Let me get a nice color here. Notice we're going from 0 to 2. So I'm going to kind of bias my graph. So there's 1, 1, 2, 3, 4, let's say. And I want to make a sketch of this guy. So my sketch, so I'm just going to graph the 2x minus 1, and then I'm going to take the absolute value of that graph. And I'll talk about what that looks like in a minute. Oops, I didn't do any y's. Okay, 2x minus 1. So that's a y. This is slope-intercept form. If you don't know this, you need to get a tack hammer. Bop yourself on the head because this is unacceptable. So I've got my y-intercept at negative 1. I'm going to rise 2, run 1. Rise 2, run 1. And so on. And I'm not my greatest graph in the history of the world, but you get the idea. Okay, that's the graph of 2x minus 1. But we want the absolute value of that graph. So what that does is it just takes all your negative function values and makes them positive. So let's try, how about a purple here? So now I'm going to take this and I'm going to, these are all positive values, so those are going to stay the same. These then are going to flip up like this. Okay, so now I want it, not my best drawing. I should have hit that. That would have been a lot nicer. Okay, so remember, we're trying to figure out the area under the curve. Now we've got this. This is the actual graph of absolute value, the one in purple. The one in blue was before I absolute valued it. So we want to find the area under the curve between 0 and 2. Maybe this green will show up. So that's this little spot here. And then we're going to 2, and that's this spot here. Well, if we just integrate this, we've got a problem, because the integral of this, first of all, we don't know how to integrate absolute value. And second of all, if I integrate 2x minus 1, that's going to give me this area that would become negative. We don't want that to be negative. So what we're going to do instead is we're going to break this graph up. We're going to break it up into two sections that are orange, I guess, that are, so I don't have to take into account the absolute value. So when does the absolute valueness change? It looks like it changes at 1/2. And if you're not sure, we can actually solve this. Oops. 2x minus 1 equals 0. Bump over the 1, divide by 2. My 0 is at 1/2. So this graph changes from being a downward sloping graph to a positive. That's when I change my value there. So I'm going to take this interval and I'm going to this integral, and I'm going to break it up. I'm going to break it up from 0 to 1/2 will be my first area under the curve. But what would my function be? Well, it would be this graph, but negative. So it's this graph multiplied by a negative. So my function would be negative 2x plus 1. Or if I wanted to, I could take that negative and throw it out front. You could also do it there too. It doesn't really matter. Dx plus, so this is the area of that little piece there. Now we need to find this area. So that's going to be from 1/2 where we left off until 2 of, now my function as is going to be fine there. Okay, I'm going to pause. Think about that again. Talk yourself through it and then try to integrate this. All right, let's see how you did. So this would be, boy, I'm going to run out of room real fast. Negative 2x squared over 2 plus x from 0 to 1/2 plus negative 2x squared over 2. I like that. Minus x from 1/2 to 2. So those are gone. Those are gone. I'll do that in a different color. Those reduce. Those reduce. Plug and chug. So what's 1/2 squared is 1/4. So I've got negative 1/4. Plugging in here, plus a half. Minus, now this is just the first grouping. 0, oh, that's easy. That's going to be 0. Plus. Okay, let's see how the second grouping goes. So I'm plugging 2 in there. Wait. Why did I make that a negative? That shouldn't be negative. Sorry. Okay, so 2 squared is 4 minus 2 minus, and then my second group would be 1/2 squared again, so that's 1/4 minus 1/2. Okay, I got a feeling some stuff's going to happen here, but I don't want to mess with it right now. It's too much for me. So if you want to try to see stuff cancel, go for it. So minus 1/2 plus 1/2, that's minus 1/4 plus 1/2 is 1/4. Minus 0, that's gone. 4 minus 2 is 2. Minus 1/4 minus 1/2 is negative 1/4, so that's going to become positive 1/4. Which then, let's just make this common denominator right now. That would be 8/4. So 8, 9, 10/4, which would be 5/2, which would be 2.5. Any of those would be fine. What do you think? Hopefully that made sense, because, I mean, we're talking about, yeah. So go back if you're not sure about that. Rethink why we needed to just make our sketch when these other ones we really didn't need to. I want to go back up here. I don't think I left myself a big enough note here. I want to really highlight that. I don't know if I made that important enough when I first did it, but when you integrate 1 over x, you got to have an absolute value in there.